Hello and welcome to today's webinar presented by Delubal Software. Today we'll be working in our structural analysis and design software, RFEM. The topic for today's presentation is CSA O86 2019 CLT Building Design in RFEM 6. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the US office and I'm located in Philadelphia, Pennsylvania. My colleagues Alex Bacon and Siska Cho will be your moderators, answering any questions you may have. They are both technical support engineers, also located in our Philadelphia office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the presentation. You can do so within the same dialog box. If by chance we don't get to all your questions, we'll certainly send you a follow-up email afterwards. So to quickly go over the content that we'll cover over the next hour today, I do want to give a brief introduction to the RFEM 6 program and the available add-ons for mass timber design. We'll then move on to our first example, which will be shown over here on the right-hand side of a CLT floor, where we'll take a look at the gravity-only analysis and design. We'll talk about the modeling and loading workflow, the design according to the CSA, including the ultimate and serviceability limit state, but recently released is also the fire limit state. And at the end of this example, we'll quickly take a look at the modal analysis to determine the natural frequencies and vibrations of our timber floor. We'll then move on to our second example. This is going to be a CLT hybrid multi-story building. This is where we can address both lateral and gravity analysis and design. We'll take advantage of the building model add-on that will release these building-specific features within RFEM, including diaphragm, shear walls, and of course, we can still carry out the full design of our CLT panels according to the CSA standard. So for those of you not familiar with our program, RFEM 6 is the base software. So this allows us to fully model our structure. All of the materials, the cross sections from the available standards are included in the base program, not only for Canada, the United States, but also other international standards. We can fully load the structure and we can get an analysis, so internal forces, deflections, and so on. However, if we want to model CLT panels to individually define the layers for a user-defined layup or to import in the CLT products from the various manufacturers, we will need the multi-layer surfaces add-on. This will make more sense as we go through our examples today. The timber design add-on allows us to carry out the full design of the timber members and the CLT panels according to that CSA standard. Now, finally, we do have some optional add-ons. In the first example, we'll take a look quickly at the modal analysis to again calculate the natural frequencies of our timber floor. And in our second example, we will be looking at the building model add-on. So we'll begin in RFEM today that when you begin a new model, the base data dialog box would be available to us. So we would give it a model name. Now for my timber floor, we could technically model this in a 2D environment since we're looking at gravity only, but I will keep this in a 3D environment. Under the second tab for the add-ons, these are the available add-ons within RFEM that you have purchased for your license. And for today's example, we're going to activate here the multi-layer surfaces as well as the timber design add-on. And finally, under this third tab, this is where we set our standards. So you'll notice that within this dropdown, I do have the NBC selected, that this is specific to wood. Now, this is identical to the NBC load combination generator above it. The difference here is that when we activate the timber design add-on, we have the ability to account for the creep factor. I'll show this to you later on in the serviceability load combinations, how we can account for that, but the NBC wood is required then when we activate the timber design add-on specifically. We will carry out the design of the CLT panels according to the CSA O86 2019, but notice we also have the NDS, Eurocode, and other international standards available. I will be working in metric units today, but we can always change this to imperial units. If we access the unit settings here, we can either toggle between metric or imperial. So I already have the timber floor modeled, but let us run through the workflow that we would typically go through when we are modeling a new CLT panel. So we would start by drawing a 2D surface element. So this would be available up here in our toolbar. And the program is asking us to initially define a thickness. So if I go into my thickness definitions, we would create a new definition type here. You'll notice that the thickness type can be set to layers. So this option is only available because we have activated the multi-layer surfaces add-on. Without this add-on active, we would not see this option available to us. So under the second tab, this allows me to individually create my layers for my custom CLT layup. To begin, we would want to define here a new material. So we can access our material database with the button up here in the upper right-hand corner. And using our filters on the left, we can filter to Canada, to timber, and then the CSA O8619. So here are all of the relevant materials with the sub-materials shown over here on the right-hand side. So once we select any arbitrary material for our example today, we click OK. Now, it would be quite common as well for CLT, of course, to change the material model to orthotropic. So this would be required because we're using this material for 2D surfaces. Therefore, we need two different strengths in two different directions. So we'll go ahead and toggle that to the orthotropic linear elastic. Now, we would also want to activate here user-defined material. And the reason why it's also quite common with CLT that we would set the modulus of elasticity in the weak axis direction to 0. So once we have input in this information for the material, it will be brought in to the thickness dialog box where we can set the thickness of our first layer to something like 40 millimeters. And the orientation is set to 0 degrees. This is based on the local x-axis of the surface element itself. Now, the second layer, we can just choose this same material. We can set the same thickness. The orientation, though, would be set to 90 degrees. And then for our third layer, we will just use this same material, again, 40 millimeters. And here we have a custom three-layer CLT layup. Now, this is the entire concept here of CLT to ensure that these layers are oriented 90 degrees from the layer above or below it. We can save this to our library so that we can pull open this layup definition for any future RFEM models. Now, alternatively, if we want to take advantage of our manufacturer library, we can do so. So you'll notice here that under the import layers from library, and to clear the filters of the regions, we have all of the manufacturers from North America and from Europe implemented directly within RFEM. Filtering to the region of Canada, we have a few manufacturers here, including KLH, Kolesnikov, and Nordic Structures. So for example, today we'll take advantage of Nordic Structures and we will choose a 7-ply layup. When I click OK, you'll notice that all of these layers are automatically brought in with the relevant thickness and orientation. And this is just information that we were given directly from the manufacturer. So quick access here if you do plan on using one of their products. Under the third tab, stiffness reduction. So this is a really important topic when it comes to our CLT panels. You'll notice that the K33 reduction factor here is for the torsional stiffness. We also have the K88, which is the in-plane stiffness reduction factor. And these values were already given to us by the manufacturer. Now, it's quite common for most of these CLT manufacturers to not include glue at the narrow edges here of our boards of each layer. So inevitably, the shear stresses are also not going to be transferred to those narrow sides of the board. So this is the reason why we typically would want to apply these reduction factors to our panel. Now, when we reference the CSA or the NDS, there really is no guidance on how to calculate these stiffness modification factors. So therefore, we actually refer to the EC5 and in particular the Austrian Annex, which has very clear equations on what these reduction factors should be when we do not have glue at the narrow edges. So I'll actually turn to our website here, deluwall.com, and we have a frequently asked question. It's FAQ 4119 that discusses this topic further and exactly how to calculate the K through 3 and K88 reduction factor here from the EC5 standard. We also have the Excel file you can directly download from the FAQ here. And if I pull open this Excel file, it's fairly straightforward in that we would just input in some properties here of our CLT panel, and then those equations from the Austrian annex are already listed here to calculate what those reduction factors will be exactly. So again, going back to RFEM, when you are taking advantage of the manufacturer CLT products, these values have already been set and given to us from the manufacturer directly, but if you are creating a custom CLT layup, this is likely something that you're going to want to input in yourself. Now, K44 and K55, these are going to be the shear stiffness reduction factors. When we take a look at the CSA O86 or the Canadian CLT handbook for deflection calculations, these all utilize the shear analogy method to calculate the reduced bending and shear stiffness to account for shear deformation. Well, RFEM is actually utilizing what we call the laminate theory, and it's going to directly calculate the shear stiffness matrix entry D44 and D55 directly, considering both shear and bending deformation. So the laminate theory is certainly a more detailed and exact approach when we compare it to the analytical equations from the shear analogy method. But point being that that reduction is all taking place underneath the hood with the laminate theory calculations, that we likely are not going to adjust these factors. Then we have our settings down here where we can activate this checkbox designed for failure of net section and failure include contact surface. So we might be wondering, well, what is this related to? So I'll go back to the PowerPoint here to explain this in more detail. This all has to do with the shear failure modes that we're going to present to you within the CLT design according to the CSA standard. When this option is unchecked, we will only check failure mechanism 1, and this is going to be the failure parallel to the grain of the cross section. If you refer to the Canadian CLT handbook, once again, section 3821, the handbook does go into much more detail about these 3 different failure mechanisms and when they should be applied. It does refer to this first mechanism as the gross shear failure. Now, when we turn on this option, we're going to carry out 2 additional checks, including the failure mechanism 2, which is failure perpendicular to the grain of the net cross section. This is also known in the handbook as the net shear failure. And finally, we also have failure mechanism 3. This is the failure of orthogonally crossing boards, otherwise known as torsion. So we might apply these additional shear checks when we have a CLT panel that's acting more like a beam, or certainly for wall elements. So you'd want to refer to the handbook to decide if that's something that you would like to activate for those additional checks of the CLT panel. The plank width would also be defined when we turn on this option, as well as a plank width including any gaps if those were available. This information would be needed then to carry out these additional shear checks. For today's example, I'm going to leave this unchecked, so we should only see failure mechanism 1 in our results. The final tab here is going to be the stiffness matrix. So this is the entire concept of this multi-layer surfaces, that we are calculating this global stiffness matrix automatically for you based on the individual layers, and we can actually view the stiffness matrix here. I'll discuss this in more detail later on when we're running our calculation. So once this information is input, we would draw our CLT panels. And you'll notice that, again, I've taken the liberty here to model 3 panels side by side for our timber floor. Now, it's really important, in the same way that we orient members with a strong and a weak axis, that we do the exact same thing for these timber panels. So CLT panels also have a strong and a weak axis, and we want to ensure that we are modeling them correctly as well. So under our navigator and the views tab, up at the top, we have our surfaces tree, where we can activate here the display of the layer directions. And I'll turn this into wireframe view and zoom in here. So now you'll notice that layers 1, 3, 5, and 7 for our CLT panel, which is the strong axis direction, are oriented in the lengthwise direction between supports, which is exactly what we'd like to see. And then those the weak axis, so layers 2, 4, and 6 are oriented in this transverse direction. Alternatively, we can activate here only the resultant, which is going to show you the strong axis orientation only. If we needed to make modifications to the axis direction, we could double click on a surface or multiple surfaces, activate here specific axes, and under this second tab, we have the ability to rotate the local axes or maybe set them parallel to a line within the model or additional options here. So I'd also like to go over the additional elements that are modeled here for my timber floor. You'll notice that we do have glulam beams that are going to span between these supports and essentially will inevitably support the CLT panels above them. Now, I did not model an eccentricity here. Everything is modeled at the center line. This is a bit more of a conservative approach with the internal forces rather than modeling this fully rigid eccentricity that may be hard to achieve in true construction methods anyway. So taking a look at the cross-section definitions quickly, we have our first beam over here, a slightly larger section at 240 by 440 millimeters, and then the rest of the beams are going to be 160 by 320 millimeters. All of these members have a moment release applied at the member ends, as well as a torsional release applied at one end only. Now, these were modeled as separate segments here. It is entirely possible to keep it as one continuous member, but if they are separate segments, it's really no problem in the program. We can select both of these and create what we call a member set. So that's what this very faint dotted line is around both of these segments. And member sets can be fully designed as one continuous member as well, regardless if the beam is broken up into separate segments. Now, we won't be looking at the member design today, rather our focus is only on the CLT design, but I thought that was worth mentioning. You'll also see here several support conditions, and essentially this is a timber floor that is modeled at the elevation 2.75 feet in the vertical direction, or sorry, 2.75 meters in the vertical direction. So these support conditions are going to represent the columns and the wall elements that are framing up underneath it. But because we're only evaluating and analyzing the specific floor for gravity only, we're representing those by the support conditions shown. So for example, we have pin supports here, and over on the right that maybe represent the column framing up into the timber floor directly for point supported CLT. Then we also have the pin line supports that are going to represent our concrete shear walls. And then you'll also notice these nonlinear line supports. So the nonlinear line supports are representing our CLT shear walls that maybe exist framing up into this timber floor. So I have set this nonlinearity here so that these two elements will release in tension. When that occurs, we also have the nodal supports modeled at each end of that CLT shear wall. This represents some type of tie or strap to take those tension forces over. So the modeling overview is complete, but now let us talk about how everything is connecting together. And specifically, we'll start with the timber panel to panel connection here. So as it's shown as default, all of the member forces the CLT panel forces and moments are going to be fully transferred to one another. But we know that these panels will likely be connected with screws. So we would like to release something like the moment. Maybe we want to account for the slip of the screw connection. Well, we do so with what's called a line hinge. And this is available over here in our navigator. Under the Types for Line folder, we can right-click here under Line Hinge to create a new definition type. And within this dialog box, we can fully release the moment between the two panels. Now, for my example today, I'm actually going to just set this to a very small value. I get a little bit better stability once we get into the larger 3D model. So it's entirely possible to release it for most scenarios, but in others, you may need to just set a very small spring constant here. We also can define the slip of the connection, and this is based on the local axes of the line element itself. So in this longitudinal direction, the local x-axis, we can define a spring constant here, and this would be calculated outside of RFEM just depending on the type of screw connection we have. So using an arbitrary value here of 8,000 kilonewtons per meter squared, we can set this in both the transverse direction, but also the longitudinal direction. So we see both the X and Y axes indicated here in our image, and that's what we're setting this slip over here on the left-hand side. Now, once we have defined this specific definition type, we would need to actually apply it to the model. So we can do so by initially clicking on our surface, and then my second click is going to be the line elements themselves that I want to apply this line hinge. So when I complete the first surface, we'll go ahead and choose the option over here to add a new object where we select surface number 2, and I'll go ahead and turn this to wireframe view. And then my second click is going to be these line elements here on the right-hand side of surface number 2 to apply the line hinge. So once this is done, I click OK through these dialog boxes. And what we should see if I turn this into a rendered view is the line hinge symbol. You'll also notice that I did apply this to only one side of the CLT panel. We do not apply a line hinge to both sides. The reason why is that this can cause instability issues within the model itself. We need to leave at least one CLT panel fully fixed. This is the same concept for 3 CLT panels framing into the same line. We can release 2 of them, but we need to leave at least one as fully fixed. Now, we have this same topic of conversation for how the timber members are connected to the CLT panel. Currently, everything is rigidly connected, but we want to account for likely this screw connection. So instead of a line hinge here, we're going to apply what we call a line release. And this is available under the special objects tree. We see here line releases. So panel to panel connections, we can use line hinges. Panel to member connections, we can use line releases. We create a new definition type, and to begin, we select here the degree of freedom definition. Now, this should look very similar to line hinges in that we can release the moment or set a very small spring constant. We can also account for the slip here between the member and the CLT panel. This may be a different value, such as 5,000 kilonewtons per meter squared, just depending on our connection. And perhaps I only want to apply the slip in the longitudinal direction here along the line length. So when I click OK, I'd like to select here my first 2 surfaces because I would like to release my beams from those initial 2 surfaces. Then I can graphically select my line elements. So I'll scroll in here to select the lines of my first beam. I'm going to purposely skip my second beam, and I'll go ahead and apply this to the additional beam line elements shown here in the rest of the model. So once this is complete, we click OK. The program says, hey, wait a minute. In order to correctly apply this line release, we need to apply either action 1 or action 2. We'll go ahead and apply action 1, and then we get the line release symbol shown around those members. Now for this second beam here, we're going to right click to create a new line release again, but this time we're going to release surfaces 1 through 3. So we're using the same definition type here, and then I can graphically select these 3 lines. And you'll notice that this is different because this beam spans across all 3 CLT panels, whereas the other beams only span across surfaces 1 and 2. So our line releases are now complete. I did want to also point out a new feature here under rigid links that can also take the place of this line release. So we've recently added the ability here to add in a rigid link for a line-to-line connection, so something similar to a beam to CLT panel. And you'll notice that the line hinge definition type is already available here within this dropdown. So this is an alternate method. If you prefer this over the line release, you can go ahead and take a look at that new feature as well. All right, so now the modeling is complete. Let us review our loading. Now, for this example, we have a very simple loading scenario. So gravity loads only. We have here our dead load, which includes self-weight only, no additional loads applied. We also have a live load. So this live load is going to be 2 kilonewtons per meter squared, just basic surface loads applied to the 3 CLT panels. Now, in reality, of course, we would have much more complex loading, many more load cases, but for example, today, this will be sufficient. Now, for these 2 load cases and for this model in general, remember we're at an elevation here of 2.75 meters in the vertical direction. And we're going to assume that this is part of a multi-level story structure. So we likely have additional stories above it that we need to take into consideration all of the loads that are being transferred down through these additional floors to the current floor that I'm designing, because the loads that I have applied now certainly do not do that. Well, I would like to take advantage of a feature that we have over here under our load wizard that allows us to import the support reactions and convert them to loads within our current model. So if I pull open a second model here, this is an identical timber floor. The only difference is that I have increased the height of it an additional 2.75 meters to represent the floor that's above this one that we're currently designing. Same loads are applied, the dead load and the live load. And once we run the calculation, what we would see here are support reactions. And these support reactions are at the nodal supports and also along all of these line supports. So this is the information for both the dead and the live load cases that I would like to transfer into my current model and convert them to loads. So going back under our current model, we can activate here under the load wizards the import support reactions. Now this option will only be available under a couple conditions. Number one is that additional model that I just opened, we do need to run the calculation and save the results to our computer. So that is required. Number two, the current model as well as the model that we're bringing in the support reactions must both exist under the same folder, project folder within the Delubal Center. So we just want to make sure that those are within the same folder together. So we want to bring in the reactions from the model that I just showed you. And the program has already detected the support reactions from the additional model. Well, in order to bring in those reactions, we need to tell the program where exactly to place them on our current model. So we want to select all of the nodes that those support reactions should be applied to as loads. And this is actually quite easy to do if I go ahead and select my options here under the Project Navigator. I can turn on within the graphical visibility here the nodes that only have a support applied. So everything else is hidden in the background. And this way I can go ahead and highlight all of my nodes here. We'll go ahead and make sure that we have selected all of them. So you'll see them highlighted here in pink as well as the node numbers given to us in this dialog box. Now we want to do the exact same thing with our line elements that currently are supported here. So I'll graphically select this, we'll turn off our nodes and instead activate the lines that currently have a support applied to it, whether it's linear or nonlinear. And we select all of these line elements. You'll notice everything is highlighted here in pink. So basically we need a 1-to-1 ratio of how to bring in those reactions and which nodes and lines to apply them as loads within our current model. Under the third tab here, we can tell the program, do we want these line loads to be uniform? Do we want to smooth them out, or do we want them to be varying? We'll go ahead and leave these as varying. So we're going to take the loads from load case number 1 of the model I just showed you, the separate model, in the global Z vertical direction, and we want to transfer them to load case 1 in the current model, so dead load to dead load. We also want to transfer the live load from the additional model in the global Z direction to the live load in my current model. So once all this information is set, we can click OK, and we just get kind of an arbitrary view here of the loading. And I'll go ahead and turn off the surface loads just so that we can see this. But when we run a quick calculation, all of these reactions will be brought in here in the background. If I kind of drag this down, we see this generated here in the background. So we'll let this move through the quick calculation of the live load only. And before we go through our results here, let us just compare these reactions to the forces. So here we have these downward forces from the model above it, around 25 and 22 kilonewtons for these two nodal loads here. Well, if we jump back to our previous model, floor number 2, that's sitting above it, and we take a look at the live load, sure enough, here are those reaction forces around 25 and 22 kilonewtons. So this can be a really useful feature, again, if we're trying to project these loads down to additional levels here. Okay, so that covers the loading considerations. Let us go into the load cases and combinations to talk about design situations and the load combinations in general. Now remember, we are generating these according to the NBC would because we want to take advantage once again of this creep factor. So if you do want to set this to a value other than 1.0, you can do so here. This is a feature we have new in RFEM 6. We didn't previously have this in RFEM 5. Under the design situations, the program will generate 2 design situations by default, the ultimate or our factored load combinations from the NBC, as well as our serviceability or our unfactored load combinations. And if we click this little info button, we see how that creep factor is directly integrated into the serviceability load combinations. I'm also going to create a third design situation here that's not created by default, and I'm going to select the fire option from my dropdown. So there are separate load combinations from the NBC that will be used in the event of fire design. So this is a new feature again that we added for CLT design. So it's really powerful what we can do. So if we want to take advantage of that, we can create this third design situation here. And notice that all 3 of these design situations will eventually be used within the timber design add-on, and this will make more sense once we get to it. Under the load combinations, you can see here the individual load combinations listed out that belong to those 3 different design situations. Everything is run according to a second order analysis considering P delta effects. So before we run the analysis portion, maybe one more thing that we would want to check under calculate mesh settings, we can adjust our global mesh here to maybe something slightly more refined, such as 0.4. We can regenerate the mesh and to take a look at it. And keep in mind too that of course mesh refinements are possible for any of these lines or nodes or maybe individual surfaces as well, but everything will be meshed automatically according to the global mesh otherwise. So we can technically carry out the analysis, but the big advantage of RFEM 6 is to work through both the analysis and the design as one continuous workflow. So I'd like to talk about the design input here specific to the CSA standard for our CLT panels. If we double click on these three different panels, you'll notice that the design properties is automatically activated down here. So this is just telling the program that not only do we want to carry out the analysis with these CLT panels, but we'd like to also carry out the design according to the CSA within the timber design add-on. Now, if we uncheck this, we see here multiple tabs disappear, and this is simply telling the program that we don't plan to carry out the design. Looking at the design configuration. So under the ultimate configuration, we do have a default setting here, and we'll jump immediately to our surfaces. You can see that we have a new conservatism factor that has been added here within RFEM 6 specific to the CSA. So when we refer to either the Canadian CLT handbook or the CSA O86, there is a strength modification factor set at 0.85, and this should be applied in the bending strength strong axis direction. So again, something we didn't have in RFEM 5 that is now included here within RFEM 6. Taking a look at the serviceability configuration, again, for our surfaces, this is where we set the limiting deflection ratios for either surfaces that are supported at both ends or if we have a cantilever CLT panel. And finally, our new fire resistance configuration. So if we go into the detail settings for this, notice we can carry out fire design for members, but focusing here on surfaces, we would want to input in the required time of fire resistance. So using our drop down, maybe we modify this to 45 minutes. Now you'll see here a value of 3 millimeters. So if the fire causes the CLT layer to be reduced to anything less than 3 millimeters, it's completely omitted from the calculation. We can also override this as possible. So if the fire does, again, char completely any of these layers, the true cross-section reduction and reduced stiffness is going to be used within the analysis. So it's really important to understand that we're not going to use the same internal forces from the ultimate or serviceability configurations, but rather we will determine which layers are fully charred or partially charred, rerun the calculation with this new stiffness. So really powerful what we are doing with the fire design. If we have any fire protection at the top or bottom of the surface, we could activate that here within the configurations as well. Under the deflection tab, is this panel supported at both ends or is it a cantilever? And then also for our reference length. So what do we want to use for our length with those limiting deflection ratios? We can use the maximum boundary line of the surface, the minimum boundary line, or we can manually set this. So in my case today, maybe I want to take advantage here of my measure tool, where I can simply measure the distance between my nodal supports, for example. So 4.8 meters. I'd like to use that for my deflection criteria rather than maybe the full length of the panel, as that would be very conservative. And finally, we have our timber design types here, the service conditions. We do have a default setting here. So for our panels as well as our members, if we were designing them, are they dry? Are they wet? Are they treated? This all just affects the adjustment factors as well as the capacities or the strengths of our elements as well. So now that the configurations have been applied to this structure, we'll go ahead and turn off our mesh here and turn this back into a rendered view. Under the timber design add-on within the table, this is our input data. So we'll see here again those three design situations, ultimate, serviceability, and fire, that we just simply need to tell the program which limit state checks to apply according to the CSA standard. So ultimate to ultimate limit state, serviceability, I'm going to toggle this down here in my drop down to the total load to check my deflections, and of course our fire design situation will be set to the limit state of fire. Under the objects to design, currently everything's selected. We're not going to design our members here, but we will go ahead and design these three surfaces. So we're now ready to carry out the calculation. Now this does solve quite quickly, but it's worthwhile here to jump back to the PowerPoint just to explain in a bit more detail what this multi-layer surfaces add-on is doing specific to CLT design. So if you remember, when we created our CLT layup, we had input each individual layer, and this is true even for the CLT manufacturers that are brought in, and each individual layer has its own stiffness properties, modulus of elasticity, shear modulus, and therefore each layer has its own stiffness matrix. So utilizing this add-on in the laminate theory, the program is actually going to calculate the overall stiffness matrix of the panel for us. So this is the really powerful part of RFEM, is that you as a user aren't having to go in here and to manually determine what the stiffness matrix is for each panel, but we're going to do this for you. And again, through the laminate theory, here's a sample calculation for the D11 entry, considering all of the individual layers. Once this is determined, we export this back out to RFEM, we apply the loads, we run the calculation, and for each one of these surfaces, we're going to get internal forces. And from these internal forces within the surfaces through a series of equations, we're going to determine the stresses. And we're further going to take those stresses and distribute them back to each individual layer of our CLT panel. So when we look at something like a 5-ply layup, we might see the stress distribution looks something similar to this. And these stresses are what we are going to compare to the CSA design equations to ultimately get a design ratio on the CLT panel. So going back to RFEM here, our calculation should be finished, and you'll notice that we are seeing our design results here in the Timber Design add-on. We can view the design ratios for each surface. So looking at surface number 1 that's closest to us, we see a series of design checks for ultimate limit state, fire design, as well as serviceability. So sure enough, if you remember back to the PowerPoint, we see that shear check failure mechanism 1 here. Another common question is, do we check rolling shear? Yes, we do check rolling shear, and in our case today, this is actually the controlling design ratio. This would be shear in the YZ plane. So we can activate what we call the design check details. That is going to show us line by line here exactly how this design ratio for rolling shear was calculated. We can see over on the left all of the adjustment factors that were considered and the values along with code references. The other helpful advantage here is called the diagram in surface point. So currently this is a cross-section view of the design ratio of the 7-ply layup, but we can use our drop-down to check the stresses as well. So if we're interested again in those rolling shear stresses, as we would expect, we see those highest stresses here in these center layers. We can also take a look at the normal stresses or the bending stresses here and see how they look, again, referencing the cross-section of our 7-ply layup. So once we have taken a look at the rolling shear in table format, design check details, everything's available graphically here as well. So currently we're looking at a ratio envelope of all design checks, but we can activate the rolling shear check 3010, but keep in mind too that we need to specify the relevant layer that we're looking at. So we're most interested in rolling shear in layer number 4. So if we activate that, then we're going to see our results shown graphically here. Moving on to fire design, and also keeping in line with those rolling shear checks, we can take a look at the design check details here. So really the same concept, but something really important to note here is the charring depth. So we can actually see which layers are completely omitted because they are fully charred from the fire conditions that we have set. We can also see which layers, in this case, layers number 2 and number 6, that are going to be reduced due to the fire. So once we determine this information, again, we've lost layers number 1 and 7, and then 2 and 6 are reduced. We are going to export out that stiffness back to RFEM with the reduced cross-section dimensions as well, and we rerun the calculation to get the new internal forces with that reduced cross-section. So again, something that's really powerful going on here with those fire design checks. So now that we have covered the basic timber design, let us back up also to the analysis. If we drop down to one of these load combinations here, and under my navigator, I can actually toggle back to the static analysis. So currently we're looking at the global deformation here of our CLT panels under these gravity loads, but we can also access the surface results. And maybe we're interested here in viewing the stresses, and we'll take a look at the normal stresses in the positive direction here. So we want to also align the stresses with which layer we're viewing of the CLT panel. So we also see that option here within our navigator. So for positive stresses, we probably want to activate layer number 1. When we activate the negative normal stresses, we likely want to activate layer number 7. When we're taking a look at shear stresses, we probably want to activate one of those internal layers, such as a layer number 4. So you can see how these stresses go hand in hand with the relevant layers that we can toggle back and forth between. The final thing to mention here that relates to the analysis is the releases option. So if you remember, we have these line hinges and these line releases. It's possible to view the internal forces of these elements as well. So for example, our line hinges, our panel to panel connections, we only have gravity loads in this case, so we can view the shear forces in the vertical direction between these two panels. So we're currently viewing them graphically, but we also can right click here on the line hinge itself to view what we call the results diagram. And I'll go ahead and empty out all of these diagrams, and we scroll all the way to the bottom here where we can activate that same information that I was just graphically viewing. So this would probably be the forces that we would want to design our connection to. So again, that's nice that that's available both graphically as well as in that result diagram. The other quick thing that I just want to mention is a general modal analysis. So I'm going to go through this again rather quickly, but we do have additional webinars like the NBC response spectrum analysis. It's going to go into much more detail on something like the modal analysis. But point being, I just want to show you today how to quickly run this to determine the natural frequencies of this timber floor. So if we go back to the base data, this is the same dialog box that we had at the beginning of this example. We can activate here the modal analysis add-on. Under these standards, we would want to select here as well the NBC 2020. We click OK. And now under our load cases and combinations, I'm going to create a third load case here that's going to be our modal analysis, where the analysis type modal is selected. I do want to import in the masses for the modal analysis, considering both dead and live load. And in order to do this, we need to create what's called a mass combination. The program can automatically do this for us if we create a new design situation for effective seismic weight. We're not going to use this in the timber design add-on. But what this allows me to do now is to automatically create this mass combination under the load combinations, considering both dead and live load. So now going back to my modal analysis load case 3, I can import in the masses from this mass combination. Under the modal analysis settings, I'm really not interested in anything in the X and Y direction. I really just want to look at the mass matrix in the global Z direction or the vertical direction. And we can quickly run this eigenvalue analysis to take a look at the first 4 mode shapes of our timber floor. So once this is done solving, we will see here our first 4 mode shapes that we have solved for presented to us, as well as the natural frequency. So for mode shape 1, we have a natural frequency of 11.4, mode shape 2, 12.1, and so on. So these values are likely what we're going to be used to determine if we need to take a look at additional vibration design, maybe outside of RFEM. But the modal analysis will certainly give us this information to begin with, including the natural frequency for each of the mode shapes. Okay, so now that we have taken a look at this gravity only of this timber floor, we're going to move on to our second example today. And this is going to be a multi-level story structure here. And it might look a little bit overwhelming at first, but if we take a look at a single floor element here, and I create a visibility and I zoom in here, you'll notice that this is the exact same timber floor that we just designed. The only difference is that rather than modeling all of our nodal supports and our line supports, that I have actually modeled in the true CLT shear walls. We also have concrete shear walls and columns framing into each one of these timber floors. So again, definitely related to the previous example that we just fully worked through. So just to explain this a little bit further, you'll notice that this is a hybrid structure, as I mentioned, because we do have additional concrete shear walls. So if I activate here just to show you the concrete material, we see these concrete shear walls, concrete core modeled, as well as our foundation slab down here at the bottom. So it is possible to fully design these hybrid structures, whether it's steel, concrete, CLT, all within one program in RFEM according to the Canadian or US standards. What else you will notice is that my lateral loads have also been applied. So we have the same dead and live load that we saw from the previous example, but we now also have a wind load applied. And this is just a simple line load, as you can see here, applied at each story level. So pretty simplistic load application for today, but again, we just want to account for that lateral load applied to the entire structure. So I want to begin by activating our building model add-on. And this is just going to release building specific features within this general FEA modeling. So we'll go back to the base data here that we saw in our previous example, and you'll notice that the building model is something that we can activate down here in the lower left corner. When we do so, at first glance, really not much changes with our model specifically, but over in the navigator, we now get a new folder here called Building Model. And this allows me to specify the specific building stories. So I'll right click here to create a new building story. Now the program automatically suggests that I would like to create my first story at an elevation of 2.75 meters. So that's correct. We'll go ahead and leave that as is. But I'm going to continue defining the additional stories here the entire way up. So we have a total of 10 stories. Now we see a nice view here showing which elements are attached to which specific stories. It's also shown in table format as well. For each one of these specific stories, we have the floor modeling options shown here within this dropdown. So the first option is really no input at all. So essentially, we're going to use the true stiffness properties of the CLT timber floor for both in plane and out of plane, so both gravity and lateral analysis. Alternatively, if we decide that we meet the criteria to consider our CLT as a rigid diaphragm, we could also set that here within the building model, and that's what we're going to move forward with today. So this is going to consider infinite stiffness in the in-plane direction, but out of plane for those gravity loads, we're still going to use the stiffness properties of the CLT elements themselves. The third option you'll notice is load transfer only. This is otherwise known as a flexible diaphragm. We will not have stiffness in the in-plane direction. We don't have stiffness in the out-of-plane direction. Rather, these surfaces will now be used to distribute loads based on the tributary area to the objects that it essentially is attached to. So those vertical walls, for example. The other options that you'll notice down here, the nodal support modeling and line support modeling. So when we activate the building model add-on and this additional rigid diaphragm, we're going to carry out two separate calculations for each load combination. The first calculation is going to run through all the load combinations considering this rigid diaphragm with infinite in-plane stiffness. Then we're going to run a separate calculation for each load combination where we extract out each individual floor. And we're going to really only look at those gravity loads. So you can think of this almost identical to what we just worked through within the first example. So when we extract a single floor element out from the rest of this 3D model, we need to somehow represent the walls and the columns framing up underneath it with support conditions. Again, identical to what we just did in example number 1. The nice thing and powerful thing about the building model is that we certainly can set this to a fully rigid connection for our nodal supports or our line supports, which is more or less what we saw in example 1. But the building model can also calculate the true stiffness of these concrete shear walls or CLT shear walls that are framing up underneath it, or the columns, to apply this as an elastic stiffness instead for both the line supports and the nodal support. So these are the various options that are available to us. Now for our rigid diaphragm today, we're just going to leave this more or less as fully fixed conditions that we see here for the relevant degrees of freedom. So once we have defined all of these stories as rigid diaphragms, we click OK. And what we will initially notice if we zoom in here is the display of that diaphragm graphically. So the center of mass is displayed here, and that rigid diaphragm is going to connect every single FE mesh point at this floor rigidly in the in-plane direction. And if we double click on our CLT panels that we're defining here for our timber floor, you'll notice that the stiffness type was now changed to a floor slab rigid diaphragm. Again, that's only in the in-plane direction. Out of plane, we're still going to use the true stiffness properties. If we really don't want to see this display of all of these rigid links, no problem. Up at the top here under our navigator, under special objects, we can go ahead and deactivate them here. The final thing to do before we rerun our calculation is to define our sets of shear walls. So under the building model folder that we were previously under, you'll see the option here for shear walls. Well, we can right click to create a new shear wall definition. And I'll begin with my series of concrete shear walls over on the left-hand side. So we just simply select them one by one all the way up the height of the building. We can also create a second set of shear walls, and these can be our CLT surfaces. So we aren't restricted to any particular material, but really any CLT, concrete, whatever it may be, can be selected as a shear wall. What the building model will do is to simply take these 2D surfaces and sum up the internal forces and present it to us as though it was a simple member, almost like a column spanning up through these shear walls. This is going to be much more user-friendly when we're designing our shear wall, so that we can immediately see what are the total shear forces in this 2D surface, what are the total in-plane bending moments, and we'll see this in just a minute with our calculation. Keep in mind too that once we have defined our building model specific features, that back under the timber design add-on, nothing is different here from what we saw from our first example. I'm not carrying out fire design for this example, but we have the ultimate and serviceability design situations. We can select here which elements we want to design. You'll notice that currently I have the 3 surfaces for my timber floor, as well as a couple vertical walls that I'll fully take advantage of the CSA design equations for. So now that we have input the information, we would go to calculate all. Just for the sake of time, I will pull open an already saved model here where this calculation is now carried out. So we'll begin with the analysis results. So I jump here maybe to load combination 4 that includes dead, live, plus my wind load. And my results are available to me here that I'm currently looking at the global deformations, but you'll notice that with the building model, we now have 3 different options to toggle to. The first is the walls only. So we're not viewing this display here of our diaphragms because these have the rigid in-plane stiffness, but rather what's the global deformation of those vertical wall elements only. Now, alternatively, I can toggle this to my floors. So remember, we're going to extract each individual floor into a separate submodel, and we're going to apply all of the additional loads, and mainly those gravity loads are only going to impact the design of each individual floor element. So the global deformation, the vertical direction is shown here, but if I try and activate any deformation in the the translational directions, we're not going to see any results. Again, because these individual timber floors are supported with those line and nodal supports, and in the translation direction, we have infinite stiffness again. If we take a look at the surface internal forces, we can activate here, not necessarily the stresses, but maybe we want to look at the bending moments of our timber floor. So sure enough, we see bending moments MX, we see bending moments MY, but the minute that we activate NX or NY, again, those in plane internal forces, we see the value of 0 here. The third option is just going to display the walls and floors together. So if we're interested in viewing the global deformations here, maybe internal forces, the program will more or less kind of display the results of those two separate calculations together. Now, remember that we also carried out that shear wall calculation here. By defining those individual shear walls, the program will display this to us as standard members. So I'm going to activate here, I'll turn off the global deformations, we'll activate only the member forces. And what else I would like to display under my specific views is not necessarily all members, but members by type. Let's go ahead and turn on only the result beams. So within the result beams, these are going to be my shear wall results that, again, the program just sums up the internal forces for the entire width of each shear wall and presents this to us graphically here as a result beam. We have this same information given to us in table format as well. So if we take a look at the static analysis with the building model, we also have the ability here to view the results by stories. And here are the member forces in the shear wall. So in table format or graphically, again, summing up the shear forces, maybe the in-plane bending moments. So this is going to be much more user-friendly than trying to determine what are the total forces across this 2D surface element. We also can take a look at the additional tabs here given to us by the building model, such as the story shear. So I'll go ahead and turn off the display of my members here and let us cancel out this visibility mode. We want to take advantage of what we call this vertical result line. So this is just going to show us, which we can see over here on the right-hand side for one of our load combinations, the total story shear graphically as we move up and down the structure. This is the same information given to us in table format as well. We can also view the displacements of the structure, and as expected in the Y direction, we see higher displacement at the top of the structure versus the bottom. This is also given to us within table format, as well as the inner story drifts. And finally, we see here the center of mass and center of rigidity. So this information is shown in table format, but also we see the display here of the center of mass as we click down through these different stories. We can also turn on the center of rigidity. So this is calculated with those rigid diaphragms and also presented to us graphically and in table format, so we can see how this varies compared to the center of mass. Now, no need to go into the details here because we are out of time, but under the timber design add-on, we are going to get the full design of these surfaces as well. Just like what we saw with example number 1, we're going to see the ultimate serviceability design ratios according to the CSA standard for both the timber floors and our vertical timber walls. Okay, so that will wrap up our second example today, where we have taken a look at both the gravity and the lateral analysis and design together for a multi-story mass timber structure. We'll go ahead and conclude our webinar today. This presentation was recorded and will be available usually within the next day of the same web page that you registered for the webinar. Both of the models that I used in the presentation are already available on this web page that you can download. If you don't already own RFEM, feel free to request a 90-day trial download directly on the website, where you can go ahead and open up these models and test them for yourself. If you are interested more in learning about RFEM, any of the products that you saw in today's presentation, we would love to set up an online meeting or possibly even a demo with you. Feel free to contact us directly with the contact information shown here, and this is also available as a hyperlink on the GoToWebinar handout that you can download, where you can contact our sales team directly on our website. You'll also see here the information for our Philadelphia office shown in the bottom left-hand corner, our phone number given here, as well as our email address, info-us@delubal.com. We will have more upcoming webinars held approximately once per month. You can register at delubal.com under support and learning webinars. Most of you know I will tend to send out a reminder email about a week before these take place, so you can keep an eye out for the next one through email as well. The PDH certificates will automatically be emailed to all participants who were here for the full presentation. So this is a requirement of the states that we are pre-approved providers, that you are here for the full 60-minute duration in order to receive that PDH. If you watched with a colleague or you watch in a conference type setting and you yourself did not register for the GoToWebinar, but you were here for the full presentation and are wanting PDH, feel free to request that at the email address shown here, info-us@delubal.com. So again, if you yourself did not register, but you are wanting that PDH, let us know who you watched it with, and we will be happy to generate that for you. And with that said, I want to thank everyone for attending today. And as always, we hope to see you at the next webinar. Thank you.